Hello, everyone. In the previous lecture, we talked about springs, and I should tell you, perhaps I mentioned also in other videos already, that the solution, the type of movement that a spring makes, and for the solutions that this kind of second-order linear differential equation when it comes to coefficients make, is called harmonic motion. And in the previous lecture, I concentrated on undamped. Sorry, I keep writing dampened. I don't know why it's undamped. This is a typo. Let me. Damped. Okay. Okay. So let me remind you what is going on. So we have our general equation. Looks like this, and I'll remind you what all these things are. So this, of course, is as always the mass, and this comes from Newton's second law, right? This is the Newton's second law. All these things are forces. This force, well, you have to be a bit careful because there are some cancellations that happen. But this particular force is the one that we call the dampening force. This part is from the dampening. Okay, and dampening is normally considered to be proportional to the velocity. And the faster you go, the more it gets dampened. And that's just a model. Okay, in this model, that's what is. And so this C is the dampening constant. And what is this then? This K, that had to do with the elasticity or the spring constant. It had to do with how rigid or how strong the spring is, this K. Okay? And I remind you, there was a formula here also. We had that K over M is equal to G over S, where G is the gravitational constant. Let me write this G here. So this is a formula that we also will use. Now, this was very nice, this formula, in case we had no C, because then we divided everything by M, and then we, instead of knowing, so you see, in principle, you need to know both K and M, but if there is no C, you can divide by M, and then, especially, at least when this is 0, and then you only need to know S. And remember, S was the difference between the position the spring would take without a weight and with a weight. That's the difference between the two. The stretch, how much it stretches by adding the weight, how much does it stretch the spring. However, so far we didn't need the mass. Now, I forgot sometimes to stress this. When we work with a forced, so when this is not 0, we need M here. And I must admit, I forgot that too at some point. Nothing, I mean, in all the videos, it's always whatever I say is correct, I think, but you have to think of this, because when they give you the external force, they mean the force which is the force independent of mass, right? Because you have to think of this. This is a force that comes from something, God knows what, electromagnetic force or some other motor engine that is adding tension to the spring, and therefore it doesn't concern itself with what weight you hang on the spring. It says, I'm going to do this regardless of what your weight is. Okay, so this is independent of the mass, and therefore this in the formula you have mass. You have to be careful, because I still prefer to write this by dividing here by the mass here. You don't have to do this, but it might be sometimes, certain occasions it is preferable to do it this way, especially when we have to work with the characteristic equation and so on. And then in particular, this constant becomes easily calculated if you know the stretch. Okay, but this one, of course, oh, sorry, I've got my y prime. This one, of course, you have to know. Okay, let's do this first. Let's say the free damped motion. So this means that the external force is 0. Okay, so all right, and let me jump into an example rather than in the textbook. They do this whole long calculations, and then we'll talk about what happens here. I'm gonna. No. Okay, yes. Let's do an example, but not a fully example yet. So, what is this? We have a 64 weight. So the weight of the object that we attach to the spring is 64 pounds. And the stretch that it causes is 6 inches. Now, we always be careful, this means a half a foot, right? A dashpot provides a dampening force. It doesn't matter how the dampening comes. They say a dashpot here, so that is like if this would be a hydraulic system that is somehow connected to something that is in a liquid, and the liquid slows the movement down. Or you could just think of the whole thing being submerged into a liquid. And the dampening force is C. So I'm not going to give a value to C yet for a reason. We will shortly give examples where we take values for C, but let's work it out without this value for C. Okay, so let's write down the equation here. And okay, so C is a dampening, the dampening constant, or whatever you call that, the dampening force C, dampening constant C. Okay. So what's the equation? What is the mass, right? Because we will need the mass in this equation. As I said, because of dampening, mass becomes, we need to know the mass. Before that, we didn't really. It depends on what we know, but what was given to us. Which was kind of weird, right? Because it doesn't depend on the mass, it seems, some of the movement. Okay, so what's the mass here? Now remember that weight, it's kind of an unofficial formula, is GM, right? I have one more time explain. You have gravitational force that pulls you down, and we measure this on a scale, right? That's your weight. The scale gives a weight. And what is the gravitational force? Well, that is this force. It's in terms of the gravitational constant of Earth, of course, and m your mass. So if you want to know your mass, you might be curious, what is my mass? Well, divide your weight divided by 32, and then you have your actual mass. You might feel a little bit smaller now, right? Because if you divide by 32, it gets rather small. So you're kind of 5, 6. Your mass is 5 or 6. The unit here is, I've never heard of this unit, I must admit, slug. But let's not talk about the units here. Okay, so what this is, in this case, we know that the weight was 64 is equal to 32. We have to use, of course, the gravitational constant in terms of feet per second, so feet pound. You have to use always the right units here, and that's the one thing one thing where it really matters is, of course, are we using the British / Empire system, whatever, the old system, then with feet and inches and pounds, and so then we have to do 32. Using the metric system, it's 9.8 meter per second squared. Okay, so 64 is 32 times the mass, so it follows that the mass is 2. So this is an object with mass 2. So what we need now, let's write everything out. So we have now y double prime plus c over 2 y prime plus, now, okay, we have to talk about this guy here. Do we know that? Well, we know the stretch, right? They told us the stretch is a half a foot. So we know that k over m, and that's the only thing we need, right? That is g over s, right? This is this constant here, is 32. Oops. Is 32, the g again. And what is s? Well, again, a half a foot. So divided by half, that is 64. So this is 64, and that is equal to 0, right? So this is, so I said it's a homogeneous one. Now it's a free motion. So we have to find the roots of this equation. Now, since we don't know c, the only thing we can do is now really, sorry. There's not an algebraic equation, I forgot to say. We go into the characteristic equation. Sorry, I was jumping the gun here. T plus 64 equals 0. Okay, so we need the quadratic formula because we don't know what c is, so there's no way that we can factor it. But in practical, in applications, in homeworks, so of course the c is a value that we have. But there's a reason I'm not putting it in yet. So what is that? So t is equal then, Well, minus b, which is now c over 2, plus minus the square root of c over 2 square minus 4 times ac, 64, divided by 2a. Look, what I did here is, in a book, I think they do the same thing, but they leave the 2 there. I kind of don't like that. I kind of like to do this way. Okay. So, what is this now going? What is the clue here? Well, there are three things can happen, right? There's one thing can happen is that this is, I don't want to put it, that this is a negative number, and then we know what happens. If this is a negative number, then this becomes a complex number, and we know that the solution will be given by a sine and a cosine. Okay, so we get this really oscillatory behavior again. So if this is a negative number, one calls the motion underdamped, although they don't use this definition in the book, but I thought that's what they call it, underdamped. But let's focus on the two other cases, because this case that this is a negative number we have seen already, right? We know we have already encountered this in the special case when c was 0, it is a negative number, because this is not there, so it's a negative number. It's obviously clear, right? And this could be negative, it could be positive, depends now a bit on c. So let's see what happens in the other. What is then? There's another special case, namely that this quantity is 0. So remember, if the discriminant equals to 0, then we know it's a single solution, so single root. There is the plus and minus. There's no plus and minus because this square root is 0. In which case, in the single root is, we can see what the single root is. If this is 0, then we see the single root is c over 4. Minus c over 4. Okay? So what is this? When this happens, this is a special case, and we also know, I'll remind you again, but this is also a special case as far as the differential equation is concerned. So the fact that we single this out is for many reasons, but in the harmonic motion we call this critically damped. Critically damped. So I repeat, critically damped means that the discriminant of your characteristic equation is 0, means that the characteristic equation has only one solution. Okay? So, and this would be, in this case, let's work it out. When is this? So this square minus 4 times 64, that is 256, right? 256 equals 0. So we get c squared over 4 is 256. So c squared is 1024, sorry. And so c is 32. Okay? So let me see. Yes, c is 32. So critically damped in this particular, you remember I didn't say what c was, right? The damping constant. We took it general. So in this setup, you would have critically dampening exactly when c is 32. Okay, that's what this means. And then what is then the next case is that this is positive, right? And then in that case you would have plus or minus, you have 2 roots, and that's what we know before. We know also what happens there. But let me again focus on what happens in critical. So let's work out now. So suppose we are in this situation. We are critically damped. So you'll see normal problems, they say we have a system. So how would the question go? We would have an object this and stretches out that much and so on. And suppose that the dampening is critically. Okay, so from that you can find what C is. Okay, there is a formula, but I really don't want to make you learn all these formulas. Just work it out. Just work out what this discriminant is. Put it equal, whatever discriminant, fancy word for whatever is underneath the square root. Put it equal to 0 and solve. Why would you learn a formula if you can just figure it out yourself? Okay, so let's now continue in this case. What are we then? So we have now, so in other words, so if C is 32, that means that the equation, let me write it up now, C over 2, that is 16t plus 64 is 0. That's the equation that we are in. Okay, so, and this is, by the way, if we do this, t plus 8 squared. If you factor this, right, and this is what we found here, because if we know that C is 32, then minus 32 over 4, that is, is minus 8. Okay, and that's of course exactly what we feel here. T is minus 8, and this put it equal to 0. So notice that this is a negative number. By the way, no, let me not say this now. So this is a negative number. Now, what about the homogeneous solution? We know that if a critical, this is something special. When the critical equation has a single root, when its discriminant is 0, then the general homogeneous solution, so y homogeneous, is, well, we know this becomes the coefficient in front of x in the exponential, right? In general, when you have two roots, you take the two roots, but you have only one root, so what do you do for the second one? Remember this? If you don't remember, pause the video, think about it a little bit. It's x times that one, okay? So this is how our general motion looks like. And I said homogeneous here, but I should not really say this because we are in a homogeneous case. It's not that we are, later on we will have to deal with that, with the force that is not free, forced movement. Okay, so that's it. Right, so and then let's say initial condition. I didn't say this, so but say I'm doing one. The textbook gives two different. Suppose that at t equals 0, y is 1, and the velocity was 20. So what does this mean? I mean, I'm writing down the numbers here, but it's sometimes good to interpret initial conditions, right? What does it mean? That means that initially y1. Remember, just a little picture again. So this is y, and what is corresponds to 0 is exactly, so here is our string is attached here, and is exactly where the string is in equilibrium. This is the equilibrium state of the string. This is the actual length of the natural length of the string, and this was our s, right? So a little bit of, s. The quantities in here that we have. And so y equals 1 means that you take up this weight, 1 unit up, the units are feet here, so 1 feet up, and then you, positive, what does that mean? You throw it upwards with a force of 20 feet per second. Okay, so you take this object here, and then you say, whoop, up you go, and then, okay, that's what happens. Okay, so of course this is the t-axis, so the movement itself will the graph of this will be something like that, right? Okay, let's see what we get. Okay, so if t is 0, professor, t is your variable, not x. Don't do that. Always take the variable that you're working with. Don't mix variables. And then, of course, you are more critically here, right? Okay, so if t is 0, well, that is nice because then this term disappears, so I just a. So a is 1, okay. Now I have to take derivative, so y prime is minus 8a e to the minus 8t. Now this is product rule, plus b e to the minus 8t minus 8b t e to the minus 8t. Derivative of the exponential and copy the t. Okay, plug in 0, so this will be 20. And what we get is, if I plug in 0, minus 8a plus b, and then this term disappears. Okay, so a was 1, so 20 is minus 8 plus b, so b is 28. So we see that y is equal to e to the minus 8t plus 28t e minus 8t. Okay. And you might wonder how such a function, what happens really with this thing. So the sketch, the graph is properly sketched in the textbook here, but so what happens is the movement, the graph of this function. So now the same axis here, y and t. Again, there's a mistake in the textbook. They write x there. So we start here at t is y is 1, right? This is where the movement starts, and so we're throwing it upwards, and it goes something like that. Okay. So remember, at each time this measures the height, right? So the spring the spring, if you want to make the spring goes, so it will go up and then will go down, but it kind of then eventually peters immediately to its equilibrium. That's why it's damped. If it's not damped, it would go up and down, and it perhaps eventually goes to its equilibrium. In fact, we have seen, you should notice this, that when there's no external force, so free, undamped motion, it keeps going up and down. There's no slowing down. It keeps going up and down. And if you have an external force, it could have these beats, right? Remember the two pictures that I gave in the homework videos? This is not at all what happens in this case. The damn thing, it doesn't go up and down. In fact, this one never, it goes up, it comes down, and by the time it's in its equilibrium, it says, okay. In fact, it never reaches in equilibrium. This is, if you take the limit for t going to infinity, it's a bit of you have to do L'Hopital to kind of the limit in infinity, but if you're used to these things, this is 0, and this is what you get here. Okay. There's a second condition. So this initial condition there, if the initial condition could, instead of, here we threw it upwards, if we would throw it downwards, what happens then? Well, because you throw it down, it kind of is going to dip a little bit below its equilibrium, but then it's going to pull it up again and again go to its equilibrium state. So dampening, critically damped means there is no oscillation whatsoever, right? It just dampens when you, in other words, it just immediately goes to its equilibrium state, except for, of course, if you push it downwards, yeah, of course it is going to first down, but once the initial push is kind of stops, that effect of it stops, then it says, okay, I want to be back to my equilibrium state. Okay? Yeah. Okay, so that is how this works. What happens now? Let's look at an underdamped system. I don't want to do an underdamped. Yeah, let's perhaps to see physically what happens. So the same question, same spring, but we change the dampening now to C equals 2. Remember, the critical was C was 32, right? So what is now our equation? So let's look at what this becomes here. So this becomes y double prime plus y prime is plus 64, y equals 0. Let me see, is this what we want to do? Oh, sorry, C is 4. Same spring with C4, I'm sorry. That's 2y prime here. Okay, let's work out what is this? What kind of motion is this? So the dampening we have said we have overdamping, underdamping, critical damping. Let's see what this gives me. Okay, so the characteristic equation, because it's a homogeneous second order linear with constant coefficient. So we look at the characteristic equation. Now this cannot be factored because that's the quadratic formula. That is 2 plus minus 4 minus 4 times 64 divided by 2 times the 2, right? And so 4 minus 64, so 4 minus 4 times 64, that is, if you want, minus 4 times 63, that is negative, so the discriminant is negative, this is discriminant, right? We know what happens then, we get these, the solution, so we have to write this up then, okay, unfortunately the square root of this thing, so this is plus no, so not plus, why did I have a plus minus here? That was really silly, this is just minus 2, right, minus b. So minus 2 plus minus I times the square root, because it's a negative number, so I'm going to take that out, 4 times 63, okay, that is 7 times 9, so that can divide it by 2, so we cannot completely calculate it. The number is not the best choice of number, but okay, they did as good as they could, as well as they could. 2 times the 2 comes out, the 3 comes out, the I don't know why I wrote it this way, and then radical 7 divided by 2. We can divide by 2 everything, so we get minus 1 plus minus 3i radical 7 over, no, not over 2 anymore. be divided by 2. So this tells me that, remember, this is how we write our number, right? So lambda is -1 and omega is 3 radical 7. So we know that this solution, so not homogeneous, it's homogeneous solution looks like, well, what we know, this will be the cosine 3 radical 7 t, okay? And what is this? This is the exponent of the exponential that comes in front of it. So, and this is of course a times that plus b times the same thing, but now with the sign. Just go look it up again. How do we do? This is all the way in the beginning when we start talking about 5.2 linear homogeneous linear equation, second order equations with constant coefficients. Okay, and so what is this motion? This is again the motion that we expect. This is going to go up and down, right? The cosine sign makes it fluctuate. We've seen this is cyclic, periodic, but notice that there's an e minus t. What is that? The result of that will be is that the amplitude, this is the amplitude, right? Okay, there are two, I know, but let's just concentrate on one. It's basically a superposition of two movements, so of both of the same type. So the amplitude is this guy. Okay, we haven't calculated A and B yet. Let's not do this in this particular example. But what matters is that this is the amplitude. And so this means how far the up and down go. And this is, in the limit, this goes to 0 again. So let me make the picture here. This is the function e to the minus t. Okay, and what this now does is this cosine or sine, let's do the kind. Well, it could go ups. And okay, I should also make the symmetrical here, right? Symmetrically, there is this would be minus e to the minus t. So this cosine this will go. This is what we see. So we see that there is a dampening going on, right? It is dampened, so it cannot be just going up and down all the way, but it's it gets smaller and smaller. The effect is that eventually it will go to the equilibrium. But in the first case, it went. So sorry, this was really not. This was the real red indicates the real movements. Okay, these were the two real movements depending on whether you went through it upwards or downwards. Here again, I'm assuming here. Okay, I started from 0 here, but okay, it doesn't matter, right, where we start. But the picture is, it's the picture that matters. Is we get these fluctuations, this harmonic movement that we say, but it gets smaller and smaller. Okay, and then this was underdamped. So this is underdamped. They don't use this word. I don't know why, but I'm going to use it. Why not? And then overdamped. So here is what we say now. Take C to be equal to 40. So what is our equation then? So we do still going on the same equation here for different values of C. The first one was the critically damped, the second was the underdamped. Now this will obviously give you the other case. So this become now 20 there, right? So we got y double prime plus 20y prime plus 64y equals 0, the characteristic equation. T squared plus 20t plus 64. Yeah, t here in the characteristic equation is not the time. T is just a variable that we have been using when we talked about characteristic equations. So don't confuse the t here. Okay, this is just temporarily this variable that we have to write down. So I know this might be a little bit confusing because you might think, oh, these are times here. No, if you don't like that, let's call the characteristic equation. Let's use. Oh no, that's not a variable. Let's use z instead. So z, fancy z. So this is fancy z. Okay, so this is our fancy z. That's the only time when z's comes. These are now real t's. It's okay. So just to make sure that we are not mixing two different things. So I'm going to use here, therefore, do the same thing here. Let's use z as a variable for the characteristic equation, just to not conflate with other usage of t. I warned you to do that, but sometimes there's so many different things that we have to do. I'll put a little thing in there. You see, it really is a z and not. So this is the equation. Now this one can be factored. Two numbers that add up to 20 and multiply to 64, that is z plus 4 times z plus 20. No, z plus 16. Sorry. 4 times 16 is 64, 4 plus 16 is 20, is equal to 0. So we see two roots, z is negative 4 and z is negative 16. By the way, these are negative roots. Do you think it's always going to happen? Well, let's look. This equation, suppose it can be factored. We have seen that this is a positive constant. That's always. The dampening constant is always positive. This is always positive. So these are always positive constants. If we can factor, that means that we have two roots that multiply to a positive and add up to a positive. If they multiply to a positive, they have to have the same sign. They can be both positive, both negative. But they add up to a positive, so they have to be both positive. So these two numbers, if we factor, are always going to be positive numbers. Therefore, the roots, which are the negatives of those things, are negative. Okay? Just pointing that out to you. What do we know about this? So this is... what does this mean? We know now that this is overdamped. Because the discriminant is positive. Why do you know that, Professor? You didn't calculate discriminant. Well, the roots are real. The discriminant tells you whether your roots are real or complex, right? Or there is a single root. That's what the discriminant does. It's a number, okay, it does something, but it has an implication on the quadratic equation. The discriminant is positive means there are two roots, real roots. Here, minus 4 and minus 16. The discriminant is 0 means there is one real root. That was the critically damped case, 32 at that case, was it, I guess? Oh, no, forget, whatever it was. And then there is the case where the two roots are complex numbers. That's exactly when the discriminant is negative. So you don't always have to calculate the discriminant. You know what the result is from here. So what we know that the solution looks like, again, this becomes the coefficient in front of, well, t is the variable here. So we get this thing. Now, why do we call this critically damped? Well, if you would draw the map of the function, this is how this function looks like. I mean, depending on what a and b are, but it is something that goes immediately down, right? Whereas here, in the critically damped, it did have a little bit of, there was some action going on, get up and then down, or went down and went up. There's no action whatsoever in the overdamped. Whereas underdamped, there is a lot of action. Okay, so that's why this terminology. Now this is all free, so like a forced case. And I'm going to do only one example. So let's look at the case. Yeah, I don't want to do a new example. Let's stick to this example still. So we're still in this case here. So let me rewrite it again. So an object, 64 pounds. It's going to be the same equation, but I was just going to say the displacement is 6 inches. And the constant is the one that I want to use, the one that we just had, 40. Yeah, C is 40. So remember that the mass here we calculated, again 64 is gm, so the mass is 2. This is a half, so we calculated that k over m is the same as g over s, that is 32 divided by a half, that was 64. So we can write down our equation. That was, again, this was how the equation looks like in general, right? I'm just copying everything just so that we have it here. But now we have this external force here. Be careful, and we divide by the mass. This is something that you have to be careful about. So they give you this, but you have to divide by the mass when you work it out. Okay? So C is 40, M is 2, and Km is 64. So our equation is y double prime plus C divided by 2, that's 20 y prime, plus K over M was 64, y equals, and now I'm going to tell you with a force, so I'm sorry, I didn't, let me put this here, the external force I'm going to make equal to, 200 cosine 2t. Okay, this is going to be my force. Okay, so here, what do you write here? Remember, it's 200 divided by 200 cosine 2t divided by the mass, which is 2. Don't forget this part here, otherwise you get different. It would only, it's this, the mistake that you would make here would just make numbers worse. But the functions really look the same, it's just the coefficients are going to be different. Okay, and often awful numbers, but okay, so in other words, this is 100 cosine 2t. I hope that I did the example before, but sometimes I might have to change it again, but let's do it. Okay, step 1. The complementary homogeneous. Okay, so that is y double prime plus 20y prime plus 64y equals 0. So what is this? In this case, complementary homogeneous is just a terminology from differential equations, right? But in this case, what does this mean? It means there's no external force. It's a free harmonic movement. Okay, and what happens then? So we look at the characteristic equation, t squared plus 20. Oh, I was not going to use t, right? I'm going to use z here. So z squared plus 20z plus 64 is equal to 0. We factored this already, so z plus, what was it? Z plus 4 times z plus 16, right? Yeah. Is 0, so we find z is negative 4 and z is minus 16. This is really just copying everything what I had here, but now this is homogeneous. E to the minus 4t plus b e to the minus 16t. Okay. Oh yeah, initial conditions. Well, I'll tell them later. Do I have them? I forget now. Yeah, I have them, sorry. Well, let's figure it out later. So that's step 1. So now step 2. What do? Last time we discussed this. If your homogeneous solution is, now you have to look at this form of this function. Okay. In 5.4 we did the method of undetermined coefficients when this was a exponential times a polynomial. In 5.5, which we skipped because we did it last time, in 6.1, last video, we know that's something else we have to do. We have to put a cosine and a sine using this angle omega here. So I remind you, so this omega here is, so what is omega here? Omega is 2 here. We always have to be careful whether this movement interferes. It is a resonance, right? Resonance means, so resonance means that the omega that you have there, in this case, yeah, yeah, well, let me put that, is a root, yeah, not omega, of course, omega I is a root of the characteristic equation. It's omega I, right, that is really a root in characteristic equations. Now this, of course, is not the case because we have real solutions, right? So we don't have this problem here. I'm just want to point out that in this case there is no problem. It's good to know, but remember in the previous, in 6.1, in an undamped, the result is always going to be, your characteristic equation always is going to give two solutions of this form, and then it's very critical to check whether the roots of your characteristic equation are not the same as this guy, okay? Because that means that you have to propose a different solution. It's not the case here, so our particular solution can just be a cosine 2t plus b sine 2t. Okay, because this, how do we recognize this? Well, look at just a homogeneous solution. As long as this is not the same as that, we can use this as an equation. If this, of course, if this would have been, if the homogeneous solution would have this as a general solution, yeah, it's clear that this cannot be plugged in. and we can, well, it's clear that if we plug this in, we get 0, so we never can get this right-hand side that we want, like, we want to have this right-hand side, we can never get that. But we are not in this situation, so we don't have to worry about that. Okay, so we need y prime is minus 2a sine 2t plus 2b cosine 2t, and y double prime is minus 4a cosine 2t minus 4b sine 2t. And now we plug everything in our equation. Where is our equation? Here, in this one, huh? Right, we're talking about the top one. Okay, so minus 4a cosine 2t minus 4b sine 2t, and then we have to do 20 times y prime plus 20 times y prime, so this is minus 40a sine 2t. I'm going to already expand the 20 plus 40b cosine 2t. Okay, so this was 20 that, right? And then we had to do 64 times this guy. So that is plus 64a cosine 2t plus 64b sine 2t. And all this had to be equal to 100, was it cosine? Cosine 2t. So we look at compare the coefficients of sine 2t and cosine 2t. Let's see, let's do this one first, cosine 2t first. And we have a minus 4, let's underline it, minus 4a plus 40b plus 64a, and that is equal to 100. Don't forget there's another on the right hand side also something. And then for the sine, so I'm writing down just the coefficients here, right? So the sine, we have minus 4b minus 40a plus 64b, and that is equal to 0. Yeah. Somehow this is a bit more difficult. In the previous case, there was always one at least you calculate it right away, right? But here we do have a system of equations here. So let's look at the bottom one here. That is 60b minus 40a is equal to 0, right? And the top one is 60a minus 40b. No, plus 40. No, sorry. Plus 40b, yeah, equals 100. We can divide everything by 20. So 3b minus 2a is 0, and then we have 3a plus 2b is 5. Okay, what can we do here? Well, you can solve for 1, but it introduces a fraction, so I rather let's do this times 3 and this times 2 and add up. And add them up, okay? So that means, yeah, the a's and b's are, I should have aligned them, but these two add up, that is minus 6a plus 6a, that cancels out, so we get 9b plus 4b, no, what, 9b plus 4b equals 5, wait, Oh, I see what I did here. I copied something wrong, guys, and that's why, because I know it was very symmetrical. Here, I forgot my minus sign here, so this, oh no, here, this is a plus sign, no, this is correct. $60a plus 40. There's a plus here, right? And let me double check now. Did I do the derivatives correct? No, this should be a negative, right? Oh no, this is, what is this? This is the derivative, the double derivative. There's 40 times, okay, there's a minus and a plus sign there. Yeah, okay. So, okay, so, yeah, I made in the preparation I made a mistake. Instead of 5, I want to have a nicer number, but okay, it will not be as nice, but that doesn't matter really, right? We get this, so b is 5 over 13, and then we can plug this in there. We see that 15 over 13 minus 2a is 0, so 2a is equal to 15 13, so a is 15 over 26. So we find our solution. I was hoping to get a nice solution, but so the particular solution is 15, that's positive, right? Yeah, 15 over 26 cosine 2t plus b was what? 5 over 13 sine 2t. And so what is the general solution is this particular solution. Now we do the general solution, right? Yeah, you please write these things out because you write a y and then another y. So this means now with a particular plus the homogeneous, right? And so now this is what I'm going to do here. Plus 8 times, or was it, e minus 4tn. That's b e to the minus 16t. There we are. And then with initial conditions, you can then even determine a and b. But let's not do this because the numbers are unfortunately not as nice as I intended them to be. Okay. So you might also ask, okay, what does this now look like? Okay. So if there are now two parts here. So this function, of course, has this particular solution. And what is this particular? Oh, this particular solution is exactly what we have seen before. This is a superposition of two waves, of two sines and cosines, so we get a movement like this, unrestrained, okay? But then you also have this part here, and what does this part do? This makes it smaller, right? This makes, in the limit, this goes to 0, this goes to 0. So you have an effect of something that, sorry. There's no picture. I want to see here. They didn't actually graph this, no. Sorry, give me a sec here. Where can I find this? Sorry, I'm looking for. Okay, no, I cannot find it. But so the result is there's two parts here. This part, the homogeneous part, we have seen in a dampened motion in all three cases, will always go to the equilibrium, to y equals 0. Okay, that's what equilibrium was. So that's the, again, this should have been red, right? Because it's the actual movement. So this is how they actually move in the dampened case, but now with the force, the force does something to it and adds a superposition. So you get this motion superposed with that. I thought I had a graph here, but I don't have it, so you can try yourself to make a graph of this thing. And so on the homeworks, I'm going to give you I'll assign a few of these questions and we go over more of them. And then we will do one more application. Very surprising is that this whole thing with springs and so can also be done in electrical engineering and has the same solutions. So from a point of view of the differential equations, we don't add something, but it's a totally different new interpretation of what happens. So I'll discuss it in a separate video.